Hello everyone. Welcome back to our calculus based on Thomas's calculus. In our previous lesson, we studied inverse functions and learned how one function can reverse the action of another. Today, we continue that discussion by introducing two of the most important families of functions in mathematics: exponential functions and logarithmic functions. These functions appear anywhere in science, engineering, and technology. Perhaps the most interesting fact is that logarithmic functions are the inverse of exponential functions. Let's begin by understanding why exponential functions are so important. Many quantities in nature do not change by adding the same amount over equal time interval. Instead, they change by multiplying by a constant factor. This type of behavior is called exponential growth or exponential decay. For example, a population may double every few years. Money in saving account grows through compound interest. Radioactive materials gradually decay over time. The spread of infectious disease often follow an exponential pattern during the early stages of an outbreak. In physics, radioactive substances decay exponentially, allowing scientists to estimate the age of fossils and archaeological discoveries. In computer science, exponential functions are used to analyze algorithms and computational complexity. In artificial intelligence and machine learning, they appear in activation function and optimization model. Unlike linear function, exponential function can increase or decrease very rapidly. Now let's define an exponential function mathematically. An exponential function has the general form f of x equals a to the power of x, where the base a is the positive constant and a is not equal to 1. The variable appears in the exponent, which distinguish exponent functions from power functions. For example, in the function x to the power of 3, the variable is the base and the exponent is constant. Instead, in the function to the power of x, the base is constant and the exponent is the variable. Common examples include 2 to the power of x, 3 to the power of x, 10 to the power of x, and e to the power of x. Amongst these, the function e to the power of x is especially important because it has remarkable mathematical properties and play a central role in calculus, differential equation, probability, and many engineering applications. Notice that every exponential function passes through the point 0 and 1, since any positive number raised to the power 0 equal to 1. Next, let's examine the domain and range of exponential function. One of the first questions we ask about any function is what value are allowed for the input and what values can the output take. For an exponential function, the domain consists of all real numbers. This means we can substitute any real value for x, whether it is positive, negative, or 0. The range, however, is quite different. The output of an exponential function is always positive. No matter what real number we substitute, the function never becomes 0 or negative. As x becomes very large, the function grows rapidly when the base is greater than 1. On the other hand, as x becomes very negative, the graph approaches x-axis without ever touching it. This means that the line equal to 0 is called the horizontal asymptote of the exponential function. These observations about the domain, range, and asymptote behavior help us understand the shape of the graph for studying its important properties in the next part of lesson. Now let's look at the graph of several exponential functions. Notice that all exponential functions pass through the points 0 and 1. Although all exponential functions share this common point, their behavior depends on the value of the base. When the base is greater than 1, such as 2 to the power of x or 3 to the power of x, the function increases as x increases. The larger the base, the faster the graph rises. On the other hand, when the base is between 0 and 1, such as 1/2 to the power of x, the function decreases as x increases. This behavior is called exponential decay. As we observed earlier, every exponential graph remains above the x-axis and approaches to the horizontal asymptote y equal to 0 without ever touching it. These graphs help us visualize two important ideas: exponential growth and exponential decay, which appear in many real-world applications. Now let's summarize the most important properties of exponential functions. First, exponential functions are continuous. This means their graph have no break, gaps, or jump. Second, they are differentiable, so we can compute their derivatives. These properties will become very important when we begin studying differentiation. Another important is that every exponential function is one-to-one. Each output corresponds to exactly one input. Because of this property, every exponential function has an inverse function. If the base is greater than 1, the function is always increasing. If the base is between 0 and 1, the function is always decreasing. Finally, exponential functions never change sign. Their values are always positive. These properties explain why exponential functions are among the most useful and well-behaved functions in mathematics. Before introducing logarithms, let's review the basic law of exponent. These rules are probably familiar to you, but they are extremely important because the laws of logarithm are derived directly from them. When multiplying powers with the same base, we add the exponent. When dividing powers with the same base, we subtract the exponents. When raising a power to another power, we multiply the exponents. Finally, when raising a product to a power, the exponent applies to each factor. These identities allows us to simplify complicated exponential expressions and will soon help us derive the corresponding logarithm rules. As we continue, you will notice that logarithm transform multiplication into addition, division into subtraction, and powers to multiplication. This makes logarithm powerful tools for simplified calculations. In the next lesson, we will naturally extend these ideas by introducing logarithmic functions, the inverse of exponential functions. We will define logarithms, develop their fundamental properties, and see how they provide a powerful way to solve exponential equations. Thank you very much for watching. If you find this video helpful, please give it a like, share it with your friends, and subscribe to the channel. Until next time, keep thinking mathematically.